Okay, guys, let's get started on topic 5.1. We're going to break 5.1 into two lessons, as you will see. And you can also see the format here is a little bit different. I was playing around with presentation styles over the summer last year. And this is what I came up with, but this is kind of a one-off. It took forever. Okay, let's proceed. First, our learning objectives are to identify two forms of charge and the direction of the forces between them. You will also be able to solve problems involving electric fields and Coulomb's law. So let's talk about electric charge. So first, charge can be generated by rubbing objects together, and you guys probably already know this. Second thing is that charge can be either positive or negative, and you probably also know this. Charged objects exert a force on each other, and I bet you know that as well. Okay, so like charges repel while opposites attract, and you should recall this from grade 10. So you have a couple of examples here in the diagram. We have plastic rubbed with wool, and glass rubbed with silk. And you can see that in our first example on the left, both objects have the same charge and therefore repel. And in the example on the right, those objects will have opposite charges. Okay, so a few key properties of charge. First, we need to discuss quantization. Quantization of charge means that charge is distributed on an object as a multiple of a discrete packet of charge. Okay, so that is a tiny packet, and we call it the fundamental or elementary charge. Again, this charge can be either positive or negative. And here it is. This is the elementary charge. This is in your data booklet. It is a fundamental constant. It is given as E, 1.6 times 10 to the negative 19 coulombs. Get used to this number. You may want to store it in your calculator as E, capital E, because it's going to come up a lot. All right, so electrons will have a negative elementary charge, and protons will have a positive elementary charge. So you can see this value as plus or minus. And the unit of charge is, of course, the Coulomb, which brings us to Coulomb's law for electric force. So the existence of this force was known for centuries, not a new thing, but it was mathematically quantified by Charles Augustin Coulomb in 1785. And he discovered these important relationships. First, force is inversely proportional to radius squared. Second, force is proportionate to electric charge, or as you can see in this equation, the product of two electric charges from two objects that will be experiencing a force. Okay, next we have the data booklet formula for electric force, and there it is. So combining those previous relationships as well as one new value. So that new value is Coulomb's constant. Okay, and you can imagine experimentally that you could set up a graph and you could pull Coulomb's constant from the slope of a graph. Okay, so Q1 and Q sub 2 are point charges where the charge is concentrated at a single theoretical point. And R then is the distance between those point charges. In the real world, the single theoretical point would just be the center of the object. So experimentally, this is kind of easiest to figure out with spheres. So charged spheres. All right, so the magnitude of Coulomb's constant is 8.99 times 10 to the 9 blank. I would like you to pause the video now and find its unit. Nice work, you did it. Okay, so there it is. The Coulomb constant, K, is equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Okay, here is another fundamental constant, and this is called the permittivity of free space. So when we're talking about the permittivity of free space, we're generally talking about a vacuum. Okay, air will also have a value very close to this, although maybe not quite. It depends on the air. This is one area where humidity actually is going to play a big role. So anyway, our permittivity of free space is given by 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Wow, those units look really similar, don't they? They do. And the reason for that is because they are related, as shown here, where Coulomb's constant is equal to 1 divided by 4 times pi times the permittivity of free space. So from this, we can do a little substitution into our equation for Coulomb's force. And the new equation is given there, and I don't think I need to read it. Okay, so if we increase this value of permittivity, what do you think will happen? And under what conditions might permittivity increase? Go ahead and pause the video and think about these questions. Wow, nice work. You guys are super good. Yes, if we increase the value for permittivity, then force will decrease because they are inversely proportionate. Good job. You knew that, didn't you? Yes. Question, under what conditions might permittivity increase? Well, I gave you a little hint earlier when we talked about the fact that the permittivity given here is for a vacuum. Okay, so if we change the material through which our force is essentially transmitted, then that value is going to change. Okay, you have some homework. I will share this handout with you, and you can go from there. Wow, fast lecture. Well done, Mr. Van Loo. Okay, have a great day, guys. I will